It's TAM 2030, or probably soon to be Mechanical Engineering 2030. The labs start next week. Everything about the labs and so on is posted on the course webpage, which you can find from my page. For now, the book is only online, and I think I'll take a survey next time if people want me to print it out and sell it to you like last semester. Now, just so I get a sense of it, how many of you were in 2020 with me last semester? And how many were not? Okay. This is actually a treat for me. It's the first time I've taught both of these courses in sequence, and usually what us professors do, or maybe what us people do, is we complain about everything, and one of the things we complain about is what the students didn't learn from the professor the semester before, and so I'm going to be stuck complaining at me. So I'm looking forward to not having that experience, and that you will, for example, already have mastered free body diagrams and vectors and things like that. If you have not, or you're uncomfortable, you have time to review. The beginning of the course, we're not going to spend much effort on free body diagrams and vectors for the first few weeks, and so you have time to catch up. And then I also know many of you, how many of you are not taking 212? How many of you are taking 212? Everybody. Okay, so I think last I knew, he was planning to give you as a homework assignment the final exam from 202 as your first homework assignment. So he's also wanting you to catch up on the 202 stuff. Let's see, the last announcement is that MATLAB is going to be even more serious this semester than last semester. Some of you didn't catch up on it last semester either because you weren't in the class, or you just chose not to. And I'm going to have a review session in this room Saturday from 2 to 4. And this is going to be absolutely primitive, simple review. It's just for people who feel like they have no idea what's going on in MATLAB, or if you know precisely nothing about MATLAB, this review is for you. It's just very, very basics. And then I think in later weeks, I'll have more and more sophisticated reviews for people who are having trouble with MATLAB. Okay, so let's start with the class. Any quick logistics questions before we get into the introduction to the material and the material itself? Yes?
Are we going to need another book besides the book that's online?
No, there's just one book. And it is the second half of the book that you used last semester. Any other questions? Okay, so what this class is called is dynamics. And I personally like this class and this material more than I like the statics material, but it's a little different in that the stuff from 202 or 2020 is really directly relevant. I advertised that class at the beginning of the semester, and it's really true as extremely applied and useful. That is, millions of people, probably literally millions of people today, are using the formulas and concepts from TAM 2020, from statics and strength of materials, in designing things. This dynamics material, even though it feels like it should be all important, and I've had this discussion now with many people, including many professors, who say, oh, dynamics is very important. And I say, yeah, tell me an example. And it turns out that in industry, people do not use the material in this class very much. So the applicability of this in practice is more subtle than statics or dynamics, and more subtle in the sense that there aren't some formulas like in statics you had MC over I. The stress was the bending moment times the distance from the center divided by the moment of inertia. That gets used all the time, whereas there aren't any any special formulas that just get used all the time in engineering practice. If dynamics is used, it's either used in a simulation mode, or it's used in a more abstract sense. For example, ideas about resonance and so on are used, but without the actual formula. So why take this class? And we could argue about why, but I would say, to me, the most important reason for you guys to take this class is actually to get better at statics. Unless you want to go to graduate school and do research of the type that people do in my lab, or you want to do rather more advanced things, this is a first class in dynamics, and to do the more advanced things, you need to learn more than you can learn in this class. Nonetheless, it's fun what you're going to learn here. You'll build skills, build your brain muscles. It will build your conceptual understanding of the world. And I don't know, I like it, and I think some students like it too. So hopefully whoever, which one of you are, will like it. So one thing to think about is, when you want to think about dynamics, is what's the relationship of statics to dynamics? So we'd like to think about how these are related to each other. And one thing we have is free body diagrams, and free body diagrams are the same in both subjects. The way you draw the free body diagram, the way you think about the free body diagram, it's the same in both topics. Now, some people like in their dynamics free body diagrams to include something they call an inertial force or inertial reaction force or D'Alembert force. That's a different church than I subscribe to. In the church I go to, we draw the free body diagrams the same way as statics and dynamics, and we do not include so-called inertial forces. Another thing is, if you do harder problems, especially 3D problems, but even 2D problems, you need vector skills. And whether those are graphical vector skills or algebraic vector skills, they're basically the same skills in both statics and dynamics. We're probably going to lean a little bit more on the vector skills in this class than we did in statics. So you probably could have got through all of 2020 and maybe even got an A by resolutely refusing to learn how to do vectors. Probably that won't be true in this class. So it'll be, I tried to get you up to speed with vectors to help you with this class, and so hopefully you've taken that to heart. And if you haven't, you still have time to learn this. Now, in statics, our basic equations were that the sum of forces were equal to 0, and the sum of moments, say relative to some point, is equal to 0. And in dynamics, what we have is that the forces do not balance. So in statics, we call this force balance, meaning the forces have to add to 0. And what's the idea is that the forces add to 0 if there's no acceleration of mass, or if the acceleration of mass is negligible. And in dynamics, we have that the forces add up to what makes the thing accelerate. And you can call that mass times acceleration, or you can call it the rate of change of linear momentum, L for linear momentum, as opposed to H for angular momentum. So on the angular momentum side, we're going to have that the sum of the torques, or the sum of the moments relative to some point C, doesn't add to 0, or they don't add to 0, but they add to something about how much the rotation, the inertial rotation increases in time, the rate of change of the angular momentum relative to point C. So the key things are that we have this idea of linear momentum and angular momentum, which varies from point to point, just like the moment of a set of forces varies from point to point. The angular momentum varies from point to point. So these things are new. Now, what goes on with that dynamics column, which we don't have in the statics column, is paying attention to that linear momentum and angular momentum. And the key thing is here is this little dot, and the dot is a notation where when we put a dot on top of something, that's a notation which means the time derivative of what's on the inside, which means that we have to pay attention to time derivatives. So right from the get-go, the very basic equations we're working with are differential equations. They're equations that have to do with derivatives. Equations that have derivatives in them are differential equations. And I guess just like the beam deflection equations or the bending moment and shear equations in statics, all of the equations in dynamics are differential equations. Now, just because they're differential equations doesn't mean we're applying the methods from Math 293, 2930 all the time, but it's always there in the background. So that means what's new in dynamics is paying attention to time, paying attention to ODEs, ordinary differential equations, and then associated with motion in general is another vector topic, which mixes up both the vectors and geometry, and this is called kinematics. And kinematics means the geometry of motion. Or sometimes people say it means geometry in motion. It means how do you pay attention to how things are moved? How do you keep track of things? The most simple examples of kinematics are, for example, we have a concept of speed or velocity, and you have a sense of what that is. It's like how fast something is going. And you have a concept of position. You have a sense of what that is. That's about where things are. And those two things are related to each other. So, for example, when you say v is equal to x dot, or r dot, or you say that the acceleration is equal to v dot, or you say that the acceleration is equal to the second derivative of r with respect to position. These are examples of kinematic equations. They're about calculus is applied to geometry, or geometry changing in time. And here it's saying that these variables, which sometimes we think of as independent, velocity, acceleration, and position, are actually related to each other by calculus, and that's kinematics. Okay, so that's what the course is about. Now you say, what's the hard part here? Well, it depends on the course emphasis. But generally speaking, I think most people agree that the way most courses like this are taught, that this is the hardest part of the class. Now, what's really the hardest part, I would say, is the free body diagrams, getting your free body diagrams down. But you've mostly got that. And it's not that it's so hard, it just takes getting used to get that down. But now there's a sort of more technically hard part. Free body diagrams, it's not technically hard. It's not intricate algebra and things like that. Here, we get the things that are technically hard, that the relationships between position, velocity, and acceleration are going to turn out to be a little bit difficult and complicated for various problems where you have machine parts moving this way and that. Now, if you're only given partial information, like you're given the forces on a machine and you want to know how the machine moves, you have to solve ordinary differential equations. And as you know from Math 293, who took Math 293 already? And who is taking it right now? Okay, so you're not allowed to be in this course. You have to get my permission to do that, right? So anybody who's taking it now, and who's not taking it now and hasn't taken it yet? Okay, so those of you who are taking it now, come talk to me. Office hours would be best this afternoon. By the way, the web page has on it office hours. They might change during the semester. The office hours are most heavy on Tuesdays because homework is due Tuesday night. And we're going to start with our office hours today. So if you have any questions about the course or how you fit in, your recitations, and your math background, come to office hours today. And for example, my office hours today are 12:30 to 2:30, and that's in Thurston 202. Oh, I knew there's something wrong here. It's 102, yeah. Something like that. It's called the Conway Room. That's my office hours today. Okay, anyway, differential equations can be hard to solve. In fact, they can be very hard to solve. In fact, most often they're impossible to solve with, say, the methods you learn in Math 293. So you punt. Who watched the football game over the weekend? Who does not know the metaphor when you say you can punt? Raise your hand if you do not know that. Now, were you raised in America? Anyway, you can punt, which means that that you give up. You give up, and the way you give up is you use numerical methods to solve the differential equations, and that makes the differential equation solution not hard. So we'll show you how to solve differential equations numerically. If I might start that even today. So this is, in principle, would be the hard part, even the impossible part. But nowadays it's not so hard. You just give it to the computer, and you can solve most any differential equation pretty simply on the computer. Okay, so let's just jump right in with example, and let me just tell you where we're going to be with this example. We're going to start out for a couple weeks just doing one-dimensional dynamics, which means vectors are not going to be so important. It means the geometry is not going to be so complicated. It means the kinematics is going to be pretty simple. And this is just to get you used to the fact that we've got this new set of stuff to put into here, which is differential equations and time. And then we'll put that back together as vectors and get into two-dimensional problems and a little bit of three-dimensional problems. Okay, so one-dimensional dynamics, what are we going to deal with? We'll deal with some mass, and we're going to assume that this mass just moves in one dimension. So this moves along this line, and we're going to pay attention to how much it moves by a variable we can call x, which is how far it's gone in that direction, and maybe it will have some force acting on it, and this force is F, and because we're doing one-dimensional dynamics, vectors are not so important, but you have to pay attention to signs. So once you've picked a positive direction, say for x, it's nice to think of this as being the positive direction for everything. So implicitly, we're going to say A is positive, V is positive, X is positive, F is positive if they are going in that direction. So that we have a sign convention for everything in that direction. Now, if we want to be all fussy about it and use vectors in one-dimensional problems, we can. And it actually helps sometimes to use vectors, even though it's only one dimension, and you think, oh, in one dimension scalars are enough. Even for one-dimensional problems, sometimes it helps to use vectors to help get the signs right. S-I-G-N-S, the signs correct. Okay, so what are we going to have? We're going to have our basic equation that we're going to work with is LMB. So LMB is linear momentum balance, and that's our main equation this semester, except for this one. So this equation here we call linear momentum balance, and this equation here we're going to call angular momentum balance. And certainly for one-dimensional motion, linear momentum balance is the most important equation. Okay, so linear momentum balance, what does it tell us for this? It tells us that the sum of all the forces is equal to the rate of change of linear momentum. In this case, we have only the force F times I is equal to the mass times x double dot times I. And then if we want to take this vector equation and turn it into a scalar equation, there's only one way to do that, which is with dot products. So we take the dot product of both sides with I, and it tells us that F is equal to MA. Let me just call this A to start with. Or we could have started right with that equation, F equals MA, at least in the scalar case. It's nice for a change not being a prisoner of small blackboards. I made a special request to have this room, and they said, yeah, you can use that room because we're putting in all this new technology so we can do eye clickers. And they just spent the usual thing, I don't know, $25,000, $50,000 fixing up this room over the winter break so we could do iClickers, and they put the iClicker screen on top of the blackboard, which is just defeating the purpose of this great room. So I'm not going to use iClickers until we get another screen off to the side. Okay, iClickers. How many of you have iClickers already? Who does not have iClickers? Okay, so you have to register them. I'd like you to register your iClicker today. Last semester it dragged on and on. It was a pain in the neck. Okay. So let's do an example. Let's say we know somehow that if we look at the position of something as a function of time, it looks like that. And let's say we have these times. We have this t1 and we have this t2. And I'll say the length of that time interval is, I'll call that capital T. And let's call this variable C here. And then let's 0 here, sorry. And let's call this A here. So if we're given, say, the position is a function of time that looks like this, we could talk about then what's the velocity, what's the acceleration, what are the forces, and so on. So the basic problem we're looking at is you take some object, it starts here at 0 with the balloons, and then you move it over to here. What's the position as a function of time when you move something from one place to another? Now you could draw different graphs, like I could assume it starts here and then all of a sudden, in which case that would have been a ramp function. But actually when you take massive things and you try to get them to move, you can't get them to jump from 0 speed to a finite speed at 0 time. It takes a while to get them up to speed, and then you bring it to a stop. It takes a while to bring it to stop. So that's kind of a generic curve for what it looks like to move something from one place to another. Now, with this curve, we can draw then 2 more curves. And these 2 more curves are the velocity and the accelerations. So here we have x as a function of time. Then we can plot v as a function of time. And then we can plot the acceleration as a function of time. So what does the velocity look like as a function of time here? Well, we know the velocity is 0 down here. And then we know the velocity is 0 over here. And then what happens in between? Well, it gets pretty big, so it goes up to something pretty big and then down like that. And then you could ask the question, well, how big does it get? Well, this is the velocity. What's the peak velocity of this thing? Well, it went a distance a in a time t, so the peak velocity is something like a divided by t, but actually it's got to be more than that because it was going slow at the beginning, took a while to get up to speed, and it was going slow at the end. So probably the peak velocity is something like 2a over t. It's approximately the peak height. Now we say, what's the acceleration? That's the key thing in this class, is the acceleration. How does that work? Well, the acceleration is the derivative of the velocity. That means we need to take the derivative of this curve. What does the derivative of this curve look like? Well, it starts out with 0 slope, and it ends out with 0 slope. This has 0 slope, so the acceleration has 0 value. Then right here, the slope is very big. So now I'll come down like here. Right here, the slope is very big, so that means the acceleration is very big. Right here, the slope is very big negative. It means it's down here like this. And this is then what the acceleration looks like as a function of time. And now that we know what the acceleration looks like as a function of time, we can make a plot of the force as a function of time, which is the mass times the acceleration. And that plot will look just like the acceleration plot. It's just that the scale is different. And this is just the acceleration plot multiplied by the mass. Then you can ask about how big is this acceleration? Well, let's see. We got up to a velocity of 2a over t, and we got there in a time of t over 4. right? Sorry, we got there at a time about t over 4, so this would be approximately something like 8a over t squared. It's the change in velocity divided by the change in time. We got up to a velocity of ta over 2 in this little time. Well, it might be even 16. It might be even bigger than this. So the acceleration gets very big, and then we look at the force, it's positive and negative. So what does that mean? It means to take this and move it from here to here, I have to push it to the right, and then I have to push it to the left. Now if you look at my hand here, when I'm moving my wallet, I push it to the right, that's your right, and then I push it to the left, but it doesn't look like I'm pushing it to the left. So what's going on here? Well, it went from 0 speed, it got up to speed, and it got slower, it had to decelerate. Somehow there's a force to the left. Well, what is it? It's the friction force. I know, you knew the answer. So the friction force, so the sum of the finger force plus the friction force, it changes from positive and then negative as I push softer to slow it down. I can barely feel the difference because mostly what's going on is that this is very close to a statics problem, and that mg times the coefficient of friction is bigger than the net force it takes to accelerate this, and more or less the force I have to push this with the whole time is very close to mg times the coefficient of friction, but it's a little bigger than that at the beginning and a little smaller than that at the end, so the net force gives the mass times acceleration. Okay, yes? Well, all of these, I had lots of choices in terms of doing this ideal problem. So I could have said, let's just do the simplest problem here, and I'm going from this point to this point. What's the simplest way to get there? It's like that. Then I would have said, what's the velocity that goes with that? The velocity goes like that. And then I could say, what's the acceleration that goes with that? Well, this is a step function. I have to take the derivative of the step function, and so the acceleration that goes with that is infinite. It's a delta function, and then a delta function here, and I could have drawn this graph like so, and well, it takes infinite force to do that. Now if you don't like infinite force, you could say, well, let's make this a little smoother, it gets this a little smoother, it gets this down from infinity, and that would have worked too. And I could do it any way I want, it's just I tried to draw a sort of generic smooth curve. Now in practice, if you want to get down to the engineering practice of things, you could say, well, what's a way to keep this simple? As I could have put a box function here. Let's just do this example. So I'll just do another example the same way. This time I'll work my way up from acceleration to position. And so I'll have here position, I'll have here velocity, I'll have here acceleration. And then we're going to have our start time and our stop time. And let's just say that the acceleration looks like this. It goes up, goes to a constant value, goes down, goes to a constant value like that. Could we have done it like so? Put on a constant force for some time to get it going, and then put a negative force to slow it down, and could we have worked things like that? Now, if we want to figure out the velocity, instead of differentiating, we're integrating, because in this case, the velocity is equal to the integral of the acceleration with respect to time. And then what do we get for the velocity is it ramps up and it ramps down. And then we say, what do we get for the position? It goes up in this parabolic way, and then another parabola takes over like that. So at this point, it's hard to see the difference between the curve I drew and this one. But when you differentiate twice, you see a difference. Now, the reason I drew this is because if you want to talk about engineering practice, if you make a machine like this, even though this has finite acceleration and finite force, it has a discontinuous acceleration. And that's considered bad in machines, especially in machines that move people. And what people worry about in machines is the derivative of the acceleration. And you say, if you, I know how to make a joke out of this. if you design something that moves people around in that bad way, you're a jerk. And so this quantity is called jerk, which has to do with like it jerks things around. If you move things in this non-smooth way, so force is discontinuous, it feels bad, it makes things rattle around, and then it's a subtle issue why that's true. And if you wait a while or talk to me after class, we can talk about that. But basically it has to do with the fact that if there is a discontinuity in the force in some part of the system, if there's some little bit of play somewhere, it tends to cause parts to bang against each other. Okay, so now let me go on and do a little bit more elaborate example where we're not given one of these curves and trying to find the other. We actually want to use the laws of mechanics. So any questions about these examples so far? Okay, so now we want to do this thing of a particle falling in honey. And probably you've seen this example in physics classes and so on. So what we want to think about is a particle falling in honey. To make it more graphic, I'll make a big particle and I'll replace the honey with the air in the room. Okay, so here's a little particle, and we're in the honey here. And now you take this thing and you let go, and you want to know how it moves. Now, this moves in a complicated three-dimensional way. I don't like that. I'd like a spherical balloon. Can you guys blow up some of these and see if they come out a little? Anyone like to blow up balloons? Get a more spherical one. So what I'm interested in here is not this complicated dynamics of this thing wobbling around. I just want to watch this thing falling. So here's this balloon. It's not filled with... That's not very spherical either, no. I got to assume a spherical balloon here. So what happens is the air in this balloon weighs about the same as the air outside here. And so the buoyant force of the room air on this thing basically balances the mass of the air, but there's the rubber, which is a little bit extra, so the total weight of this thing is a little bit more than the buoyant force. So we can think of this, rather than say there's a buoyant force and there's the weight, we can think of sort of the excess weight, which is excess weight of the balloon, and then it's, if I let go, it falls. And if we do this in slow motion, what you see is that the weight is bigger than the air drag to start with. There's no air drag, so it accelerates. And then there starts to be resistance from the air flowing over this thing, and that slows it down, and so it reaches roughly a constant terminal velocity. So on top of that, it wobbles around in crazy ways. So ignore the wobbling, but now in fast motion, it accelerates, and then it falls more or less at constant speed. So we'd like to see, can we get the math to agree with that? So we draw a picture of our particle, and we pick a coordinate direction. It's easiest if we just call x positive down, and associated with that is that force is positive down and so on. So we need to just pay attention to that when we draw, when we go to write equations. We have a force on this thing which is mg. And where I write mg there, that's really a proxy for the total weight minus the buoyant force. If I wanted, I could put the total weight and subtract the buoyant force, if I was being very careful. And then we have a force of drag on this thing, which is slowing it down like this. Okay, now how does the force of drag work? Well, the faster it goes, the bigger that drag force is. So the force of drag is proportional to the speed, and it's got a constant here. Now, is that a good approximation for what the drag force is on a balloon? And the answer is no, it's not. Out here in the big world we live in, forces tend to go as the square of the velocity, and we'll work our way up to problems like that in the coming days. Okay, so we have the drag force is proportional to velocity. Really, this constant here is some other C1, and it's multiplied by some area, and it's multiplied by the density of the air. So really, you think the cross-sectional area of the balloon is bigger, you get a bigger drag force. If the air has a certain density, as opposed to water, as opposed to honey, whatever, the bigger the density of the fluid, the bigger the drag constant. Then it depends on the shape, and this is a shape factor. But altogether, for a given balloon falling in air or a given particle falling in honey, there's some proportionality constant. And in our model here, we'll assume that the drag force is proportional to the speed. So then when we go to write the equation F equals ma, take our linear momentum balance equation. This time I'll be a little sloppier. I'll go directly to the scalar notation. We have that the sum of the forces is equal to the mass times acceleration. And so we're going to have mg. Now this one, if this quantity is positive, it's going in the negative direction. So if this quantity is positive, it's going in the negative direction. So that's minus CV, and this is equal to the mass times acceleration. And then we can write this again as mg minus CV equals m times dv dt. Okay, so that's the governing equation. Any questions about that governing equation? Okay, now this is a tricky thing I've got to learn how to do this semester, is stay a blackboard ahead with erasing. One semester, the course evaluation said my favorite part of the class was watching Professor Ruina erase the board with a sponge. Okay, so here we have the governing equation for this falling balloon, and from this we'd like to figure out how does the balloon fall. Now, we could go back to these kinds of pictures like I was drawing here and just try to draw the curve of how the balloon moves as a function of time. In fact, why don't we just start out with that guess, and then working with that guess, then we'll go back and see if we can get the math to agree with the guess. So how do we think this thing works? If we just draw it out, we start at a place we call 0, it accelerates, and then it gets to some sort of constant speed. So if we plot then the speed versus time, what do we see is it starts at 0 speed, it accelerates, and then it reaches some asymptotic speed. And then what does the acceleration look like as a function of time? It starts out with a positive acceleration and then decays to something like this. Now, maybe I should have given this as a homework problem for you to work on your desks. Is this different in any way from what any of you would expect for these three curves for dropping this balloon? Yes?
The acceleration doesn't seem quite right.
The acceleration doesn't seem quite right. So let's try to rationalize that acceleration curve. What happens is you take this balloon and it's still, and I'm holding it here. Right when I let go, the only force on this is the gravity force. So there's no air drag on this yet because it's not moving yet. So what is the downwards acceleration of this right when we start? the value of this acceleration right at the start is g. It starts with a downwards acceleration of g. Then the faster it goes, the less it accelerates until the acceleration drops to 0. The acceleration has to start here, and then as it goes faster and faster, the acceleration gets less and less until the gravity force balances the drag force. Now does it look reasonable to you? So you wanted it to sort of go along for a while and then drop? You happy with it? You're not happy with it?
That's good.
Okay, any other questions? Yeah?
Would that be mg or just g?
That's just g, because what happens right at the start of this problem, right at the very beginning, we have the mass times the acceleration is equal to the mass times g, so the acceleration is g. Yes?
Well, we're assuming it's not hitting the floor.
So we have this infinite classroom. Assume a spherical balloon in an infinitely tall classroom with constant air density throughout. Okay. So now I get to the next blackboard, and I need to erase the next thing, but I keep this one. Keep this closer at hand. Now, how many of you think this is a pretty bad semester if the best part of the class is watching erasing the blackboard? Okay, so there are a couple ways to write this differential equations. And the first one is the one that I actually care about more, and this is setting it up for numerical solution. And for numerical solution, what we'd like to do is we write this as dv dt is equal to, and then we put everything else on the right-hand side. So what's everything else? We have a g minus c over mv. So dv dt equals minus c over m v plus g. Now, the other way to write this is for solving on a test in Math 293. I think this problem was probably even too simple for a test. Probably no exam question was as simple in Math 293. But if there was such a question on the exam in 293, they would have written it maybe like this: m dv dt plus c over m v is equal to g. Okay, now each of these sort of has a philosophy to it. Did I do something wrong?
Yeah.
I divided through by m in half the equation and not the other half of the equation. Okay. But you can do the same thing to both sides of the equation, but you can't do it to this part of the equation. It's not legitimate algebra. Okay, so what's the philosophy of these two things? Let me start with what you had in Math 293. The philosophy over here was you divided this into two parts, and you put this as the unknown functions of time. Unknowns on this side, and on this side you put the known functions of time. And then you see on this side we have v, velocity is a function of time, some unknown thing. Something about that unknown function of time equals something known. Then how do you go about solving this in 293 land? I'll do this in a minute. But first you put a 0 over here, that's the homogeneous solution. Then you put a constant over here, you get any solution to that. Then you add the homogeneous solution to a particular solution, and you get the general solution. Then you plug in the initial conditions, and you get your solution over here. So that's your Math 293 world, which I might have time to do a little bit. Then here's your the world that we're going to mostly live in this class, which is a different way of thinking about differential equations. So in this view of differential equations, we have functions of time, and some functions are given and some functions are known, and we're trying to find formulas for those functions of time. We're going to change our viewpoint a little bit on differential equations to say a differential equation is a crystal ball. A differential equation is something with which we can predict the future. So the philosophy is, if you know how the world works, and you know the present state of the world, then you can predict the future. And this is true in all parts of your lives. If you know the social dynamics between two people, and you know what's going on, when you leave them alone in the room, you know what it's going to be like when you come back in 10 minutes. They're going to be arguing or kissing or whatever it is, depending on what their social dynamics are. You can predict the future from the initial condition and what the rules are. And that's what we use in the laws of mechanics. The equations F equals ma, those determine the future from the present. And in the old days, they really used to think this. And somebody, I think it's Laplace, said, if you tell me where all the particles in the universe are now, I will predict all the future of the universe. The idea is if you know how all the atoms interact with each other and you know all the rules, you can predict the future. And that's the way we're going to look at these simple equations, is we say, if we know the rules of interaction of balloons with air, we can predict the future. We can predict from where the balloon is now, where it's going to be in the future. And how do we do that? Well, we say we know the rate of change of some quantity, the velocity, in terms of the present state. So we know on the right hand, we put a description of the present state. In this class of dynamics, the present state is 10:58. And I predict that as time flies by at the rate of 60 seconds per minute, it will be 11 soon. Okay. Did you see the movie The Unbearable Lightness of Being? Okay. Okay. So we want to predict the future from the velocity, from the present, and we do it this way. So how does this predict the future? It says if we know what v is at one time, we can figure out what it's going to be a little bit later because we know the rate of change of v. And then if we know what it is a little bit later, then we know that we can apply the rule again, and we know it's going to be a little bit later still. And then if we know that, we'll know what it is a little bit later still, and so on. And this is Euler's method of integration. Now, who learned Euler's method of integration in 293? Did you have to program that yourself? Or you had to do it by hand. Okay, so now you're going to, in this class, you're going to really do it on the computer, lots and lots. And you want to predict, and what you want to do is just march ahead and predict the future. What you get is some function of time. It's a list of numbers which represents the function of time. That function of time should agree with the same thing you get by formulas down here. It should be very close to it. But this is more the approach we're going to take. So I think I'll just end the class right now. Any quick questions, and I'll pick this up next time. Okay. Okay. In the movie, The Unbearable Lightness of Being, there are these two characters.